All right, good afternoon, everyone. We can take a start, please. So very pleased to welcome our next speaker. It's going to be Brian Duguid, chair of the Net Zero Bridges Group and also affiliated to Mott MacDonald. So take it away, Brian.
Okay, thank you very much. Hopefully you can all hear me okay. If you've all come in nice and happy from your break, I'm afraid it's my job to talk about carbon and climate change and bring you down very slightly and then level off and then hopefully bring you back up again. So hopefully that's what we'll do. So I'm chair of the Net Zero Bridges Group. I am also a practice leader for bridges and civil structures with Mott MacDonald. When wearing my Mott MacDonald hat, I'm part of the ERMABI steering group, so I've been following this closely. But today, just bear in mind, I'm presenting mostly wearing my Net Zero Bridges Group hat, in case I say anything controversial. Apologies, the notes aren't synchronizing on here with the presentation, so hopefully we'll manage to get our way through it. So Net Zero Bridges Group is a collective of more than 30 member organisations, mostly consultants and bridge designers, with a shared interest in decarbonising our bridge design and engineering work. And you can find out more about us and read our publications from the website that's linked on there. And if you don't note that down, it'll appear on the final slide. Okay. So again, apologies because these were synchronized earlier and now they have decided not to synchronize. See if we can get that working. Nope, and the slide advance thing has stopped working. Just
Company, yeah.
Let's
keep pressing that one.
Fingers crossed. They are, unfortunately, still not synchronized with the notes, I'm afraid. Okay, we're going to go through this and we're going to rough it, but it's going to be a bit rough, so apologies if I run over time as a result of that. So everyone who's a member of the Net Zero Bridges Group has signed one of the 3 climate declarations shown up the top left here. And as you can see, this is our mission to accelerate progress towards net zero carbon bridges by sharing knowledge and ideas and shaping best practice. And on our website, it says just bridges, just net zero. And that's to give us a focus, because quite honestly, we could just get involved in way too many things, environmental sustainability, improved social outcomes, and so forth. So just net zero, that's decarbonisation. That's achieving a balance of greenhouse gases and CO2 in the atmosphere in and out by 2050. We don't deal with climate resilience, but I will come back to climate resilience because these subjects, they don't split apart. They're not separate things, as I'm sure you know. So I'm going to talk to you today. I'm going to remind you the climate context. If there's anyone in the room who doesn't understand the climate context, great, you'll learn something. If you learn it or know it all already, it is a useful reminder. I'll talk about how that applies within construction, why construction and infrastructure are important. I'll talk about how we frame climate action within the construction industry, because that's then important with how we frame our discussion about masonry arch bridges, and I'll talk a little bit about those. And then, as Matthew said earlier, I'll ask the question, is there a future for new stone bridges? And I won't come up with an answer, but I'll at least hopefully point us in a direction on that one. So the climate context, we are in the middle of a climate emergency, and it is a climate emergency. The second word is really important. We have been pumping fossil fuels into the atmosphere for nigh on 200 years now, and we are now in the middle of the consequences, and you'll see some of that in the forthcoming slides. We've got a duty as professionals and a duty as compassionate human beings to do something about it. And our work with bridges and our work with masonry arches does not escape from that imperative. Most of you have seen this visual diagram. This shows temperatures from 1850, shortly after we really started affecting the climate, up to 2022. And it's dramatic. You can see the record-breaking temperatures that you read about in the newspapers over the last few years. What I'm interested in this graph is not what's shown in this graph at all. I'm interested in the bit that's off to the right of the screen. This is just the foothills of climate change that we're experiencing right now. It's going to get a lot worse unless we do something about it. Going to do a few graphs. It's a sort of science place, so I'm going to stick you with the graphs and the numbers. This graph is global atmospheric CO2 concentration, and you can see if you overlay those climate stripes against it, there's a pretty obvious visual relationship. More CO2 in the atmosphere, rapidly accelerating climate change, and it's very visual there. again, since about 1850. Today, we've hit about 425 parts per million. That's where we are in 2023. And we're heading up towards about 475 parts per million by about 2100, probably more. That's a 2 degrees centigrade change from pre-industrial levels. We're nowhere near that yet. We're currently sort of about 1 point something, 1.1, 1.3 kind of range. That 2 degrees is, we're going to notice that because we're noticing it already. Flooding in Pakistan. This is 30 billion pounds worth of damage. 30 million people affected, 1 million homes destroyed, 2 million people displaced, and this was last year. Wildfires in Canada. This has been burning since April. Today, I checked this morning, there are 700 separate wildfires burning in Canada, still out of control. It's the worst wildfire season on record in North America. And we're going to see more of it. It's not going to get better, it's going to get worse. We're going to see massive loss of biodiversity, environmental destruction, crop failures, loss of safe drinking water around the world, mass migration, and conflict. And coming back to that $30 billion of damage in Pakistan, the estimates from the IPCC, the International Panel on Climate Change, are for annual damage of the order of 500 times that when we seriously get out of the foothills and up into the mountains of climate change. Again, another really important graph where what you're seeing on the graph is kind of fairly obvious. These are annual CO2 emissions. 1850, United Kingdom were responsible for half of the annual CO2 emissions in the entire world. We have played a major part in this in our history. And again, what's interesting on this graph is not that obvious correlation between pumping CO2 into the air and temperatures constantly going up. It's what happens to the right-hand side of this. We need to change, and we need to change really quickly. And we are not, as I said earlier, we are not immune to that as bridge and masonry arch engineers. People will tell you, bridges, really? We need to worry about bridges in net zero? We've got electricity to worry. We've got to decarbonise the grid. Well, we're doing that. That's the blue line up there on the top of the graph, making pretty good progress. Not as good as some of our competitors, but not so bad. We've got to decarbonise transport. We've got to decarbonise buildings. Yes, we do. But all those lines along the bottom of the graph, these are the other sectors of the economy. Some of them pretty flat. Manufacturing and construction, which is our bit, falling. But we've got to get them all. Unless they all get to net zero, we are continuing to increase the global atmospheric concentration of CO2. And if we are continuing to increase it, we are continuing to increase the temperatures and the associated damage. And it does not stop until it all goes to zero, or we find some magic way of taking CO2 out of the atmosphere to balance it. So our bit, this is what we're talking about. We're playing a part in that bit there, manufacturing and construction and decarbonising it. So a little zoom into construction. Why is construction a problem? I think some of you will know about this. This another graph. I'm nearly going to finish with the graphs, hopefully. This is global greenhouse gas emissions by sector. We should not be thinking about ourselves as people who are looking at bridges. We're involved in the construction and infrastructure industry. We are looking at steel and iron. We're part of that, playing a part of that. Big sector for emissions internationally, cement. And actually that other industry one there on the top right, that is also us. That is processing all those raw materials into things that we know and use and love, like cars and computers and bridges. So our task is actually in construction, decarbonising that stuff, hard to decarbonise materials. And it's all about materials. Anyone who's done a carbon calculation will recognise this calculation here. Embodied carbon is equal to quantity of stuff and a carbon factor for that stuff, carbon per unit rate. And for the things we deal with in construction, it is overwhelmingly about production of materials, production of cement, concrete, and steel in our cases. Site logistics, site plant, transport, these things matter undoubtedly, but materials is where we're at. Our use of materials is our embodied carbon that appears on those graphs. And we're stuck with two of the worst and hardest to decarbonise materials that there are. So this is from National Highways, so their zero carbon roadmap that they published last year. On the left, concrete, on the right, steel. These forecasts, if you look at the pale blue is their forecast predicted trajectory for materials based on conversations with suppliers. So this is what suppliers are telling them they think they'll achieve. And you can see on the left, concrete, suppliers are saying by 2040, which is way too late, we'll probably get down to about half the emissions of making that material that we do today. Steel, a bit better, it's much easier in the steel industry if people invest in it. So these are difficult. And the key to addressing these is going to be using less of them, because we're not going to magic away their emissions technologically. That leads into climate action. So what does that mean we actually do within the construction industry? And bit by bit, you'll hopefully see me inching towards masonry arch bridges here. I know people want to get to that bit. We're quite fortunate in the construction industry. We've got this very good standard, PAS 2080, carbon management, buildings and infrastructure. Excellent document. It tells us what to do. It's a process-oriented document. It's really boring. It's the quality assurance of carbon. But it has within it some real gems and some real key things that people can take away. And remember, one of them being another graph, slightly simpler graph this time. This is called the carbon reduction hierarchy. So the entire construction industry should be thinking about these three things when we're thinking about what to do differently. The first one is avoid. That means avoid doing things that cause emissions, unless we have to do those things to reduce emissions. Building wind turbines, for example. You can't avoid putting steel into wind turbines if you want to reduce energy sector emissions. Switch means making different decisions, different types of bridge, perhaps, different materials in a bridge, in our case. Avoid might mean not building a bridge at all, where that's feasible. And then improve means being more efficient. So efficient use of materials, optimization, structural optimization, those sorts of things. Once we decided we're going to build it and it's going to be roughly this kind of thing, can we do it with less stuff? So they're quite a good lens to look at what we do. PAS 2080 provides the inner rings here. Lovely project life cycle. This is PAS 2080 and GRIP and RIBA all mapped against each other. And if you read between the lines in the standard, it's roughly saying best time to avoid big emissions is in the strategic definition phase of a project. If you can decide you don't need to build this project or do it in a completely different way, build a ferry instead of a bridge, you're going to avoid a lot of emissions. We can't do that. Get into the optioneering phase, look at how we can do things better, make some different decisions, that's switch. And then the rest of it, design, delivery, operation, etc., is improve. Let's try and do things more efficiently. So this is from PAS 2080. The stuff around the outside is just an interpretation of it. And I think this is wrong. I think it's particularly wrong in respect of what we're here to talk about with masonry arch bridges. So I think this is a better diagram, because actually our best opportunity to avoid using new stuff, to avoid making the decisions that generate new projects, is in that operation and maintenance phase. Keep our existing stuff valuable, keep it usable, repurpose it, recover it, revitalize it, because then you don't get into this need to build new stuff at all. And we see a lot of that in this industry, and actually we see a lot of it in the masonry arch bridge world. Bridges being infilled, renewed, replaced, where maybe they don't need to be. Let's just be a little bit tentative about it for now, can have an argument later. But nonetheless, that maintenance cycle, which is what ERMABI is tackling, and our understanding of existing assets primarily, that's our key opportunity to save loads of carbon. So you're all fighting the good fight if you're involved in that. So, masonry arch bridges. Okay, no idea where I'm at for time without my notes. Hopefully okay. Right. Let's get some pictures of some bridges on the screen, because, you know, that's what us people know and love. Things we know about masonry arch bridges, and Matthew said some of them earlier. They are long lasting. They are very durable. This bridge is over 3,000 years old. You know, it is the oldest still in use. You can walk across the top of this. You can go to Greece and walk over this if you wish to. Still in use bridge in Europe, so far as we know. There's a couple of maybe slightly older ones in the Middle East, but not much older. This stuff lasts, given the right circumstances. And we've been building it in a much more sophisticated form for a very long time. Again, this is 2,000 plus years old. And there's a couple of bridges of this vintage in Rome, if not more. The one older than this, and then this one itself. And if you look at the drawing of that, I put the drawing on rather than a photo, because this could be a bridge from 2,000 years ago, or it could be a bridge from 200 years ago. Good quality, well-built masonry bridges in the right conditions, they last. And again, this one you can go and still cross it today. And then a personal favourite from China. This is only, apologies, only about 1400 years old. But again, look at that. That's fantastic. Well built. It's probably had a bit of maintenance at some point. Sure, the parapets have been redone. But these bridges are highly durable and highly carbon efficient as a result. Because that bridge is there, they didn't need to build another bridge there. Pretty straightforward. So, masonry arch event, sadly, only so long we can glory in the past. I want to contrast it with some of the structures that I deal with in my career. And I've got a few pictures from my recent career and from some of my Mott MacDonald colleagues, just as examples. This is one up in Manchester, between Manchester and Salford, in fact. We're actually still pretty good at refurbishing and conserving masonry arch structures. This was a simple job. This was a rebuilding of the spandrel wall that you can see in front of you, the elevation of the bridge, completely rebuilt to its original 1830 form, which had been degraded over the years, and re-waterproofing and new drainage scheme at the same time. Absolutely fantastic job by the stonemasons, and this is a very slight skew on this bridge. The geometry is not as simple as it looks on there. We can do a good job when we want to, when we're motivated to do so. Literally walk 50 metres away from that on the same project, we start getting into things that become slightly less straightforward. This is a brick arch pier railway viaduct. Hamish knows this well, along with some of my colleagues. This is really quite an interesting one. This is an existing brick pier, which had cracked down the middle of the outside face and appeared to be operating as two leaves like this, operating semi-independently, with this crack down, like a sort of shear failure right down the middle of the thing. Again, you know, good luck finding that in standards that John Shave refers to, or possibly even analysing it with some of the tools that we've got today. We stuck some pre-stressing bars through it and stitched it back together. It stopped doing that and we walked away. But we might like to do better. We might like to understand a little bit more about, did that work? Was it safe? Trains were up, freight trains were running over the top of this on a pretty much nightly basis. We don't know, frankly. And many of these are the sorts of problems that, again, we have in our sort of day-to-day life. The one at the top left, if you look very, very carefully, you'll see some little black lines under the arch barrel. And again, Hamish and I recall this one very well. This arch barrel had split. I can't remember the exact number, but it's split into roughly 6 or 7 parallel rings with 5 or 6 cracks, longitudinal cracks running down the middle of it. And if you stood in a cherry picker underneath this thing, when a train went past, you would see the brickwork on the other side of the crack going up and down like this, because they are genuinely had separated. So us engineers, we love our concrete, belt and braces. What are we going to do about it? Not really sure. Let's underring it with precast concrete. Let's pre-stress the precast concrete together. Let's stitch the piers together with pre-stressing and new foundations and all the rest of it. Definitely sorted the problem of that, I'm absolutely certain. Was there anything else we could have done? I want to say no idea. We had lots of ideas. But did we understand really what was going on? We had lots of theories. I'm not sure we ever really understood what was going on. And again, did we understand whether it was safe, given that we were continuing to run trains over this on a daily basis, and it had a RA rating less than the assessment required it to have, let alone all these cracks, even before you take the cracks into account. And those pictures just also illustrate one of the other things we do. We don't just preserve existing bridge structures unaltered. Big part of our work is alterations. This was widening of the same viaduct in order to move the railway over and put a new railway junction in. All done in lovely precast concrete, really complicated stuff, as you can see on there. The interesting bit on this one was trying to work out what would happen at the interface. The original proposal for this design was to stitch it in, stitch the two in with stainless steel stitching bars. We were a bit nervous about that, to be honest. And we employed our friends at Bill Harvey Associates, and they set up all these lovely cameras and measuring poles. And gave us all these fantastic graphs of movement, vertically, movement longitudinally, and sway. The movement of this bridge, phenomenally complex, moves in 3 dimensions like this every time a train goes over it. And it gave us the confidence to deal with the interface issue in this case, so that we wouldn't damage the track or the interface going across it, and we could tolerate the movement. So this is about movement rather than about capacity, but it's actually all about understanding, about whether we understand how these things behave and whether they're safe or not. And a couple more from mine, because I wanted to bring it back to climate resilience. Many of the people in the room could put a picture up like this. This was a bridge where the pier had collapsed into the river in the December 2015 floods, which destroyed all sorts of bridges, particularly in the north of England where I work, and we did the strengthening and stabilisation scheme. And that is becoming an increasing part of our issue, is understanding flood damage, susceptibility to flood, safety under flood conditions, and whether these things can be safely rebuilt or need to be replaced. This one was safely rebuilt, I'm pleased to say, with strengthened foundations. But we're beginning to get into ones again where the theoretical understanding is really lacking for these. And this is another one in the north of England. We've had a few of these. So these are new flood protection schemes. That Q100 design flood event at the top of the parapet, that wasn't the flood level before we came along. That's the flood level that's caused by putting flood barriers all the way along the side of the river, upstream of this, in order to protect homes. Our task is to assess this horrible bridge for that flood event and work out whether it's going to remain safe with traffic going across it. Picture in the bottom middle, that's a plan view. So sort of square span in the middle, two sets of skew spans either side. This was some complicated model we've done to try and work out three-dimensional thrust lines. So taking your sort of 2D thrust line approach and rotating it to understand whether that can sort of set itself back into the piers adequately. And we analysed it a couple of different ways to decide whether this was safe or not. But our knowledge was definitely inadequate to that. And this is all under the effects of buoyancy. When it's flooded to that level, half this masonry had lost huge volumes of its normal dead load thrust because of the buoyancy. Do we know how to analyse it? Not really. Were we able to have a sensible discussion about risk with our client? Yes, actually. It's pleased to say. It's quite unusual. But work, not necessarily the ERMABI work, but this general idea of improving our understanding of these structures will allow us to give them better answers on things like this, ultimately. Use of stone. I'm not sure if this was my idea or if Matthew just threw this into the presentation title to sort of take us a little bit beyond this. So that was all about the avoid bit and the carbon reduction hierarchy, preserve existing stuff, use less stuff, brilliant. But actually, could we decarbonise the future stuff we build by using different materials, such as stone? Oh, for and against. I put this for and against thing up there, and they've all got question marks. Because we don't know, actually, is this really a good idea? We think they're very durable. The evidence is they're very durable. You talk to local authority bridge engineers, certainly the ones I've spoken to have said that apart from scour, masonry bridges are the least of their problems. That's a common refrain I've heard from several of them. So that's good. Yeah, low maintenance, etc. The carbon, we're not really sure. There's different views on what the carbon of these things are. Design standards, we've got this design standard. Hands up if anyone's used it. Design unreinforced masonry arch bridge. That was my guess as well. And we've got concerns over competence and cost and all these other things. But of course we can build them. This is North Wales, consultant YGC. These are widenings of an existing two existing masonry bridges of three that they did round about this time. Yeah, we can do it. We know how to do it. We knew how to do it 1,000 years ago. We still know how to do it, and we can do it in pretty good quality. That could have been a brand new masonry bridge rather than just a widening, quite easily. Of course we can do it. Some people will have seen these before. This is out in Tanzania, a very different sort of economic and construction circumstance. These are partially funded by the Belgian Development Agency, Enable. They've got a design manual you can see up there. I think they've done about 70 of these so far. And within that situation, it's pretty much definite that these are cheap, high social value in terms of employment, definitely low carbon, robust, durable. You know, why would they not be doing this other than some other country wants to sell them loads of steel or something like that? So it can definitely be done, and not with massively high technology. It's the classic favourite. Anyone want to guess what the span of this is? I can't tell because I've not got my notes, but I think from memory it's 150 odd metres. It's of that order. Probably certainly the last very big masonry arch bridge the Chinese are going to build. Even for the Chinese, this was getting expensive when they got to these sorts of spans. And you can see from the scaffold at the top right there quite why that is. But that's going to be a very durable bridge short of earthquake. That's going to last a long time. We're not going to be worrying about rusty rebar and concrete cancer and things on that. There are proposals for similar bridges in this country. Many people in the room will be familiar with Adrian Timor's digital stone bridge proposal. This was at, I think it's called Bridge Road in Bristol. Not sure I quite believe the slenderness of the piers on this visualization. But other than that, this is feasible. We've got the technology to digitally cut all the stonework and assemble as we're doing things a bit like that in building structures now. We know we can do it. The engineering competence is there, and maybe you just need to get on and actually give one a try. So apologies if you're just here for the arches. I'm going to slightly move away from arches, and this is moving away from arches very quickly. Things we know about stone. So this is a classic stone bridge, Punta Sorensons in Switzerland. It's not an arch bridge, or is it? You know, the stone here is restrained and pre-stressed by the stainless steel bands upon which it sits. So all the stone on this bridge is in compression, just like an arch, really. It's upside down, but never mind. And having jumped up and down on this with a load of bridge enthusiasts, it's really stiff and massively economical. What would happen if you turn that upside down? So this was designed by the great Swiss engineer Jörg Konzett, and he has turned it upside down. This is the more recent bridge, the Waterfall Bridge, and this one's been done the other way around. This again is just stone blocks, very slender arch, and it's pre-stressed by stainless steel bands which form the bottom of the parapet on top of it, pre-stressed in at either end, and it allows you to make it very slender. You know, in terms of again keeping your thrust within the arch, if that's the way you want to sort of conceptualize it. And it's a really ingenious little piece of bridge. The stainless steel band sits on these rollers, so the rollers give you a frictionless surface when you're pre-stressing it. And incidentally, they also mean you don't need to drill through the stone to support the parapet. The parapet is just supported there by the fact that it's pre-tensioned on. Another one of Jörg Konzett's bridge. This is Dorfbrücke Vals, which is short for Village Bridge Vals, for those who don't speak German. Slightly more complicated bridge. This has a reinforced concrete deck spanning between two stone beams at either side. The underside, concrete beams, lower part of the concrete beams is pre-stressed, so that's like the tie and a bowstring arch. And then the compression part of the arch is provided by these radial stone voussoirs, very thin stone voussoirs. And it was done largely for architectural reasons. And the reason it's solid is for flood protection reasons. But it works, it's fine. It'll be there for a long time. And just to finish off on the subject of arches, if you definitely really do want low carbon, the Recreate Bridge from Switzerland, a fantastic example. This is just in a lab, but there's no reason why it couldn't be somewhere else. 10 to 12 meter span from memory, 20 centimeter thick blocks, pre-stressed again, conventional pre-stressing this time, drilled through the center of the blocks again to maximize the structural efficiency, and all made from recycled concrete. These concrete blocks were cut. Disc cut or water cut from a building in Switzerland when it was demolished. And if you want low carbon, that circular economy stuff, reuse, definitely low carbon. I'm going to move briefly away from arches. No one's given me the little sign yet, so that's okay, but he's going to give me a wrap-up sign. So I'll just skim through these very quickly. If you can tear yourself away for arches for a moment, there is also a future for pre-stressed stone just in beam form. This comparison here shows quite clearly because stone is very high compressive strength, or can be, you can get some very efficient structures and very low carbon compared to concrete and steel. First proposed in the 1950s, come and talk to me afterwards if you want to argue about whether this was actually feasible or not, wasn't built. But Heinz Hosdorf, really great, a great engineer, so maybe it could have been done. And of course, these things really exist. If you want to go and see one, you can go down Stevenage. You can see Town Centre Gardens Bridge. This is pre-stressed granite. Probably a little bit more slender than you would manage in reinforced concrete. Very stiff, very durable. If you're not scared of pre-stressing, which probably means you're European rather than British, if that's the case. And this slightly more crazy example, this was in Cornwall for the Tintagel footbridge competition, Price and Myers, 70 metre span, those 100 millimetre thick stone sections, water jet cut, pre-stressed together in a shallow arch form. Feasible, but again, probably don't want to comment. But what I took from all of these is that stone is in the air. It is worth thinking about. People are beginning to think about how we might use this in a sensible way. Super quick wrap up. Climate context is real. It is an emergency. It may not be happening right out there right now, but it is affecting somebody somewhere else in the world right now. Absolutely guaranteed. Construction is a pretty big contributor to that with our use of steel and cement in particular, and we need to do something about that. Climate action for us means avoiding new emissions wherever we possibly can, rather than designing super smart structures. And avoiding new emissions means preserving our masonry arch bridges, and that means understanding them better, which is what this conference is about. Is there a future for stone? I think there is, actually. I see some of my colleagues talking about this bit by bit on the schemes where we're being asked to innovate. I see them talking about it more and more. So yes, I think there is. And if we can understand theory again better, that will give us the confidence to have the competence to be able to build those in a way that is bold and helps us fight against climate change. Thank you very much.
Thanks very much, Brian, for a very thought-provoking talk. Because of time, and it's mostly because we slightly overran coffee rather than due to Brian overrunning, I'm going to defer the Q&A for this talk to the panel discussion. So Brian is going to join that panel discussion later on. So if you've got any questions, jot them down and see if you can squeeze us into the panel discussion in half an hour's time. So instead, we're going to move on to the final talk today, which is going to be given by Lorenzo, who's going to basically tell us some of the work he's been doing on multi-level assessment.
So in my contribution, I'm going to summarize the results obtained by the Imperial team for a multi-level assessment of masonry arch bridges. The research integrates within the ERMABI project and is linked to the other part of the project. In the main, we're going to use validated high-fidelity models to generate response performance data. This is to develop an objective multi-assessment framework. So a brief outline of my presentation. I will provide a background, the context for the research. I will remind the main features of the response of masonry arch bridges and the multi-level assessment framework. Then I will summarize the main features of the computational strategies developed at Imperial. We've been using to study the behavior of masonry arch bridges. And then I will set out the scope of parametric study, presenting the geometrical and mechanical characteristics of the structures object of the study. And then I will present and discuss some illustrative results, focusing on different aspects, namely the interaction with spandrel walls, the link between 2D and 3D models, and the consideration of reduced models based on a simplified assumption for the masonry materials. So the background, as we know at this stage, masonry arch bridges are relatively complex structures featuring a 3D behavior. So in this study, we consider single-span masonry arch bridges where masonry arches interact with backfill material and spandrel walls. So we start from the main assumption where accurate models should take into account this complex interaction between the different parts. So should be able to model different parts separately and take into account the mutual interaction. So at this stage, I believe we are familiar with multi-level assessment because it was recalled in a previous presentation. Currently, we can use different strategies characterized by different levels of sophistication, where detailed models are level 3 models. We should be able to describe fully all the components and with realistic material parameters. So we use these advanced models we call in the following high-fidelity models as the starting point. And then we reduce the complexity of the model by reducing the dimensionality, moving from 3D model to 2D model. And then we simplify the material description for masonry. So this is the main focus of this presentation. Within the project, we're going also to link detailed high-fidelity models with lower level models for a more rapid assessment. So currently, the rapid assessment tools are mainly 2D. They allow for arch backfill interaction only with different level of sophistication. But in some instances, they are not conservative. So there is a need then to put forward a more consistent framework leading to a safe design. So our approach is to use validated high-fidelity models to then determine a partial safety factor for reduced models. But importantly, we use high-fidelity models also to define instances, cases where 2D models are not suitable. So it is important to stress that to achieve accurate prediction is important to describe properly the masonry as a construction material. It is relatively complex, it's definitely isotropic, and the response depends upon the characteristics of the individual components, but also on masonry bond. With accurate models, it's possible to predict complex failure mechanisms. In this case, we have typical 4-hinge mechanism, but also ring separation and shear sliding mechanisms, which can be captured only if we take into account this anisotropic response characteristic. So in this context, we can adopt different material models for masonry based on different scales of representation. Typically, we consider within a nonlinear finite element analysis macro scale models where the material is assumed as a uniform isotropic material. So these models are more efficient, but the material parameters, the calibration of material parameters is more problematic because it should be based on component tests. As an alternative, one can adopt more sophisticated models. In this case, take into account the characteristics of the constituents independently. So we have to represent units and mortar joints separately. So using what we call mesoscale models or very detailed microscale models. In this case, we can determine material properties from material tests on constituents, but the main drawback is the computation cost, because the computing time for this model is very substantial. So they are suitable for high-level simulation of a problematic structure. So after defining the context, I'm going to illustrate the developments within our group. So we develop sophisticated 3D high-fidelity models where masonry is modeled at mesoscale. We model each component, each unit, and the mortar joints, leading to a very accurate representation of the structural component. The backfill is explicitly represented as a cohesive material with friction. And also we take into account the interaction between the different parts using nonlinear interfaces, allowing separation for the different parts. As an alternative, we developed also more efficient macro-scale models. In the following, we call them reduced model, but actually they are not very simplistic because they're still based on nonlinear finite element simulation. And they are still 3D models, but in this case, we don't follow the actual bond. We use a reduced mesh, where again, the material is represented as a uniform isotropic material. So thanks to some advanced computational tools within our group, we can simulate the response of real scale structure using detailed models because we use partitioning strategies allowing for parallel computation. We divide the large structure in partition and we run each partition independently using separate processors. This will allow to speed up the simulation and to analyze also large structures. So we're going to elaborate on these concepts in the presentation tomorrow, where the high fidelity models developed in our group will be presented in more detail. So parametric study. So the starting point is the availability of a validated high fidelity models. I'm going through quickly here to some stages of the validation where we consider previous full-scale material tests. We develop high fidelity models and we simulated the response, obtaining good comparisons in terms of stiffness and load capacity. Importantly, we are able to fully represent the failure mechanisms involving not only the arch, but also the other components, like in this case, spandrel walls. So the response is fully captured in 3D, so we are able to represent the behavior of the spandrel walls subjected to the lateral pressure exerted by the backfill. In the main, the high fidelity models have been validated at large, and now they represent a unique tool to investigate the response of real structures. So within the parametric study, we use the validated high fidelity models to study different aspects of the bridge response. As I said before, in the main, we generated an amount of performance data which are important to understand the 3D behavior of the structure and to link the 3D response to the response predicted by reduced models. In the main, we analyze the contribution of spandrel walls, comparing the full 3D models where each component is represented explicitly with models where the spandrel walls are missing. In this case, the backfill is confined along the transverse direction fully, but the spandrel wall contribution in the longitudinal direction is not taken into account. So we investigated also the link between 2D and 3D models. In this case, we consider a 3D model without spandrel walls, and we link the prediction to the prediction obtained via a 2D model. It is important to stress that 2D models here is still developed using an high fidelity model. So we represent fully the bond characteristics of the masonry arch. So, and finally, we compare the high fidelity predictions against the prediction obtained using a reduced model. In this case, we use a macro scale model for masonry, a standard plastic damage model. One can use in different commercial software for nonlinear finite element analysis. So the parametric study is quite substantial. We analyze a number of realistic bridges with different span lengths, different bond characteristics. From the slide, you can see that the masonry bond is fully represented, so we can easily distinguish between stretcher bond, header bond, and different bonds for the spandrel walls. So I wanted just to pay attention to the size of the problem. Also, when we consider a reduced width of 3 meters, the size of the problem will become significantly. We're talking about models with a number of degrees of freedoms well above the million. So models which can be simulated only using superior computational resources. So about the loading. So we consider a typical axle load. We allow for the spread to the surface field, and we end up with this loading scenario where the top of the backfill is subjected to a patch load, and then the load is transferred via the backfill to the arch below. Of course, the backfill is confined by the lateral spandrel walls. And then we consider different loading positions, right? Because the 3D behavior is triggered by the position of the load. So for different width values, so not only one single width, but different width values, 3 meters, 6 meters, 9 meters, we consider a different loading position, mid-span, quarter span, mid-width, and quarter width. So we generated a large number of models, and we simulated these model populations to obtain performance data. Regarding the material parameters, we use the same material parameters adopted for model validation and obtained from material tests in previous research. We start now discussing the results we got in the parametric study. First of all, we start from the study on spandrel wall. As I said before, we consider model allowing for spandrel walls in detail, and model without spandrel wall where the backfill is fully confined along the transverse direction. So I'm showing here just one case, but in the parametric study, we generated numerical performance data for a number of scenarios. So as you can see here, the case where the load is applied at mid-span, mid-width, so quite far from the spandrel wall. If we compare the two results, red car, the model without spandrel wall, but with the field fully confined, and the dotted line, the model with spandrel wall. In this case, the spandrel wall, they provide higher capacity. When the spandrel wall start developing significant cracks, the response converges towards the behavior of the model without spandrel wall. Looking at the out-of-plane response, we can see that the spandrel wall, they don't deform significantly along the out-of-plane direction, confirming that they can provide a high level of confinement to the backfield. If now we move the loading position, the load now is nearer to the spandrel wall. So we see that we observe that we reach the critical damage in the spandrel wall for a reduced loading level. So we converge to the response of the model without spandrel wall, and we can still keep increasing the load. So this basically behavior is dictated by the out-of-plane displacements of the spandrel wall, which a certain level of displacement leads to a structural softening of the response. If now we move further, the load is applied a quarter span, quarter width. We see it now that the out-of-plane deformation due to damage of the spandrel wall becomes more significant, and the ability of the spandrel wall to contribute to the load carry capacity of the structure is reduced. So if now we consider cases where the spandrel walls have a reduced thickness, you see that we introduce a new curve, the green curve. We see that now the ultimate capacity of the structure is reduced. Why? Because we notice a nearly failure of the spandrel wall out of plane. So the spandrel wall cannot provide suitable confinement to the backfill and cannot activate a full failure mode to the arch. So this summarizes that it is important for an accurate response prediction to allow for all the components and their motor interaction, because disregarding one of the components may lead to unsafe predictions. Now, quickly, I move to the comparison between 2D and 3D models. In this case, we determine an effective width based on the load predicted by 3D models. In this case, the 3D model is a model without spandrel walls. We remove the spandrel wall contribution to enable a proper comparisons between 2D and 3D model. So the effective width is determined at the ratio between the load predicted by the 3D model and the load given by the 2D model. So the effective width in the main depends on different factors: load position, backfill characteristics, and the 3D arch behavior. So we started developing 2D models. In this case, I show you an example. And then we developed the 3D counterparts. Then for different width values, we apply the loads at different positions, and we obtain different response curves for different loading levels. This will enable us to determine explicitly an effective width for different scenarios. So this is just an example where I compare the different curves. The lower curve is the 2D model, assuming 1 meter width, and the other curves represents the response at different loading levels of the models with 3 meter, 6 meter, and 9 meter width. It's clear that higher load capacity is obtained when we increase the width, especially from 3 to 6, while moving from 6 to 9, the load capacity remains almost the same. So if now we consider the definition of effective width, there are different ways we can different strategies we can follow to define the effective width based on the numerical curves. We selected in this presentation to consider effective widths at different loading level based on the response of the 3D model. So we have effective width at peak load 80%, 60, 40, 20% of the capacity predicted by the 3D model. You can see the effective width changes by changing the level of loading. So by moving from a serviceability type of loading to ultimately limit state loading. And so the effective width changing significantly, moving from 3 meters to 6 meter width. On the other hand, there are also notable differences from 6 to 9 meter, depending on the loading level. So we conducted these checks, this calculation for the different loading position, obtaining results which, as anticipated before, depends upon the loading position, not only along the specific bridge structure analyzed. So finally, in the final part, I would like just to compare models with different complexities. Here we are talking about 3D models, 3D finite element models, where the high fidelity model based on a mesoscale masonry model is compared against a more efficient macro scale model. Again, macro scale is still nonlinear finite element 3D models. We're talking about, again, still sophisticated models, which nowadays is considered, at the top of the scale of the modeling capabilities. The material parameters, again, are obtained from the material tests used in previous model validation. So we start here a simple comparisons where the load is applied quarter span mid-width. So we compare the results, right? The red curve is a macro scale model and the blue curve is the mesoscale one. So the results looks fine, but I should anticipate that the mesoscale model consider a stretcher bond. If now I change the bond, so I consider an header bond, which is not taken into account in the macro scale model because the macro scale model is based on an isotropic description for masonry. It doesn't allow for masonry bond. We see a completely different prediction. Why? Because the stretcher bond suffers also from ring sliding, which is properly captured by the mesoscale model, but is not determined by the macro scale one. On the other hand, the header bond model, it doesn't suffer from ring separation and sliding, leading to a higher load capacity prediction. So it's important to note that the response predicted by macro and mesoscales are in very good agreement until a relatively high loading level. So it means that the macro scale model can be used with confidence at serviceability level. But if we want to predict the actual failure mode, the use of macro scale model with simplistic calibration may be misleading, may lead to inaccurate results. In this case, safe, but inaccurate results. So this is the same scenario. I move the loading position, and again, I obtain a similar prediction. Macro scale is fine. For a certain bond, I change the bond characteristics, and then the results are very conservative. It is always conservative? Unfortunately, not. So, and then the failure mode is correct, not always. So in the main, standard macro scale models cannot represent failure mode associated with a specific bond. So they require a more advanced model calibration. This is another important point. So we change the load just to explore further the potential of macro scale model, and we end up with this sort of results where macro scale model predicts punching shear failure, right? When the load is applied a mid-span mid-width. In this case, the depth of the backfill is reduced. The load is applied close to the extrados of the arch, and the macro scale model predicts punching shear failure, which does not develop according to the more accurate mesoscale model. So conclusions. So they develop high fidelity models, which has been extensively validated. As I mentioned before, model validation will be discussed and presented at large tomorrow. Provide the baseline response data for the development of consistent multi-level assessment frameworks and for the calibration of more efficient models. So then safe assessment should consider the interaction between the different components, including spandrel wall. In the main, weak spandrel wall may suffer early damage, which does not enable the spandrel wall to fully confine the backfill, and this leads typically to a reduced capacity of the integrated bridge structure. So effective width obtained in this study depends on different factors: load position, backfill characteristics, and dependently, of course, on the 3D arch behavior, as we found comparing the responses of models with different width values. And then to conclude, the use of nonlinear 3D models with simplified representation for masonry can lead to inconsistent results. In this case, within our group, we develop refined macro-scale models, an isotropic macro-scale model, and we develop improve calibration strategies, which improve the prediction, enabling us to calibrate macro-scale model, which provide a closer prediction to the high fidelity ones. So this concludes my presentation. Okay.
When the spandrel God, that doesn't sound like me at all. When the spandrel wall moves outwards, how did that affect results, especially where a longitudinal fracture can develop under the spandrel wall, separating the arch barrels into, let's say, 3 separate arch barrels? How did that affect stiffness or deflections?
Yes, yeah, sure. Very clear. So I can go back to one of the previous slides. Sorry. In the main, so if then, for instance, in this instance here, right? So we compare 2 cases. The same bridge, but the spandrel wall has 2 different thickness values. In one case, is thicker, and the other cases has a reduced thickness. So in the second case, the spandrel wall gets early damage because of the pressure exerted by this backfill, which is a soil material. So we push the backfill down, and then it expands laterally. So it pushes against the spandrel wall. So in this case, we have an early damage in the spandrel wall, and then it means that the spandrel wall cannot provide an effective confinement to the backfill. And so we reach a capacity without obtaining the same response as in the case of more solid, more substantial spandrel walls. So in terms of modeling, as I told you before, so we model the different components separately, but we model also their interactions. So we introduce computational devices, nonlinear interfaces, which enable separation between the parts. And these nonlinear interfaces take into account the frictional response, the frictional interactions between the different components, backfill, spandrel walls, and arches. Okay.
I think it's time for one more question, sir. If we just question over there.
Thanks, John Gocher from Tony G. Just wondering, you're talking like with the different failure mechanisms there, with the different bonds and overall both the punch and shear. Do we need, in practice, looking at those failure mechanisms when we're coming to the capacity of a result and be able to look at different factors and how then relate that to actually what the actual capacity is compared to the model capacity, if those macro scale models aren't realistic to have kind of
So I mean, in this example, I wanted just to to put a flag, right? Just a warning. So using, let's say, sophisticated models, nonlinear finite element models, not always leads to, accurate results. When you use for masonry macro scale models, typically, standard macro scale models you use in commercial software packages, material properties calibration is essential. So in this specific case, if you want to model properly the development of cracks along the radial joints, you need to assume a tensile strength, for instance, for the masonry, similar to the bond strength, right? But that assumption may lead you to wrong prediction for other type of failure modes. Because, in typical macro scale models, tensile strength is linked to the shear strength. You cannot define independently the shear strength from the tensile strength because it's linked. Masonry is linked to the bond, right? The interlocking behavior, which is not properly captured by macro scale model, where masonry is represented as a uniform isotropic material. So in practice, it's important to understand the limitation of the models and to be able then to use different model tools in an appropriate way. On the other hand, here we're talking about a complex response. Too simplistic models may lead to unrealistic results, which are difficult to control. Okay.
Okay. Thanks very much, Lorenzo, and thanks very much for a very interesting talk and Q&A. All right, we're moving on then to the last part of today's session. So we have a panel discussion. It's going to be a little bit shorter than we planned. It's going to be chaired by Vasilis, and if the other members of the panel could please make their way down to the front, that would be appreciated. So we have Vasilis Sarhosis from the University of Leeds, Brian Duguid, who we've already heard from, Bob Humphreys from CSS Wales, and Kafui Klutse from Network Rail. And the topic of the discussion is identifying key industry needs.
Thank you, Matthew. So I hope you are enjoying so far the workshop. The way we're going to run this panel discussion is as follows. We're going to have like two phases. First, we're going to ask the panelists to introduce themselves and then respond to the question on their industry needs. And then it will be like an open discussion for everyone to interact. So I will start with Brian.
Okay, thank you. So you know who I am because I presented earlier and gave you a bit of an indication of the sorts of problems that particularly bother me. I think in terms of key industry needs for me, I think it was interesting, Matthew, I think your statistic earlier was that nearly half of the bridges in the UK are masonry arches. So it's a huge proportion of them, and I can't remember what number you gave, 30,000 bridges or something like that. And they are still our least understood of all the existing bridge assets that we deal with by a substantial margin, I would think, quite honestly. I think the real issues are for clients making decisions that are economic and justifiable. And I think, we see lots of examples where the easy answer is to do something. We've got a bridge that's a problem. Let's just knock it down, rebuild it, infill it, close the road, whatever. And that's perfectly understandable. And I think sort of largely a mechanism of cranking the handle on the assessment calculations and not actually having anything better, no better tools or no better theoretical understanding to turn to. So I think that's the real thing. We need something much, much better to make decisions. And our theoretical knowledge is nowhere near adequate for that.
Hi, I'm Kafui, Principal Engineer Structures for Eastern Region. So obviously the railway, we have about 28,000 structures, 60% of which are masonry viaducts. And the challenge for us is how we effectively manage these assets. Obviously, there are analysis packages out there, but in terms of how they accurately predict the capability of these assets is one of or accurate prediction of capability of these assets is of concern to us. You don't have to look too far to see the issues around funding, and with aging asset stock, condition deteriorates. You can't willy-nilly replace structures as you want to. So how do we stretch these assets further? And that plays into the narrative that Brian was talking about earlier on sustainability. The competencies around that are challenging. How much effort goes into eking out capacity but not pushing these structures beyond where they can comfortably sustain loads. Obviously, for all of us, we want to catch our trains from point A to point B, arrive on time. When things do go wrong, it goes horribly wrong. And for us, we see all of you as customers, and therefore you need to have confidence that the railway will deliver when it needs to deliver. Now, for us, consistently, the issues we tend to have is objects falling from height. So it might be pieces of brickwork falling. We might have, or we have had, instances of significant structural distress. I don't know how many of you know about 9 Elms 2 Christmases ago, where a whole spandrel wall came away from a structure. We had a similar incident in Scotland as well, where again, basically unzipping of a spandrel wall. And for us, incidents like that is a harsh reality of the safety challenges that we have, and making sure that our customers, you and everybody else, travel safely on the railway. So through this research, how do we equip engineers with the right information to be able to predict capability? But then also for us, how do we predict the onset of damage so that we can put appropriate measures in place to arrest it? And those are the sorts of things that we want to ask for support through this research. Thank you.
Yeah, so Bob Humphreys, I'm principal engineer for YGC. That's a consultancy arm of Gwynedd Consultancy, and we do a lot of masonry arches, both for our internal clients and for the trunk roads in North and Mid Wales and other neighbouring authorities. I think industry needs for us a driver for sort of revisiting assessments of masonry arches, because they've all been done before, a majority have been strengthened or okay, is abnormal loads, because sort of BD 86 and CS 458 have come along. So a lot of the original assessments were just looking at the assessment loading and didn't look at abnormal loads. So a 3D tool that can deal with that comprehensively is what we need. My colleague John referred to a structure it's actually on the junction, so the load path over the structure is complicated. It's quite a sort of long arch, so sort of the 3D version of limit state, if it had a load path function, so it could be more than just straight over, that would certainly simplify the assessments. Another thing for in North Wales particularly, I suppose other parts of the country, a lot of our arches are stone, so the random masonry. And I know that the research so far has been based on sort of ashlar type and sort of talking about stretcher bonds and stuff, but a lot of them are just random masonry with lime mortar. And I mean, that's probably another area of research, but whatever outcome of this research is, it will be used for those sorts of structures. So even if we can't sort of bottom it out, any sort of fudge factor that might be needed to apply to that, rather than sort of engineers just guessing, would be useful. Thanks enough.
Excellent, thank you very much. So to summarize what the panel have already mentioned is they talk about that we already have a vast majority of masonry arch bridges in the UK. Most of them are deteriorating, they are suffering potentially effects from climate change. So Brian talked about the net zero construction and the importance of that. Kafui mentioned about the safety issue It is important to bring trains from A to B, but what happens in the between? Safety is also a route aspect, is not only an individual bridge. So it's like moving from A to B, how safe is that? And then Bob referred to the 3D tools that are essential and providing a better and more realistic understanding of the behavior of these bridges that are vital. I would like now to open the discussion to the floor and ask anyone that wants to discuss something, anyone that wants to refer to make some further comments. I can keep this one so I can.
Hopefully you can hear me. Yep. Niall Mackay from Atkins. So we've heard a lot today about the multi-level assessment process that the ERMABI project's been involved with, and jumping straight to a level 3. And I just wondered what the panel's thoughts were as we operate in a commercial environment. So that's either limited budgets for clients actually being able to deliver this type of work through, and certainly from my experience of being a consultant of competitively tendering for this type of work, what the scalability of jumping straight to a level 3 assessment actually is.
Do you want me to chip in? We're not suggesting that you do a level 3. We're suggesting that we're using level 3 to calibrate model factors used for level 2 and level 1. So hopefully Lorenzo's talk didn't try to persuade you that the only way is level 3, because that wasn't the intention. So we're looking at the cases when a 3D model will be very, very useful and maybe essential, and other cases when it's fine. At the moment, the problem is uncertainty. We don't know clearly what the limits are, and one of the things we're looking to do is bottom that. Anyway, I should pass it to the panel because I'm not supposed to be on the panel. Anybody else wants us? Yeah.
Yeah, well, I mean, the way I would handle that is when I quote, I say we're doing a level 1, and then escalate it as necessary. Yeah.
In relation to West Trevorwood from Ireland, we've got a huge number of masonry arch bridges. I think the factor is actually significantly higher than it is in the UK. But we've got a problem that we're still using the older codes. We've also got another issue that PS has even talked about, whereas it would be very handy. And then we've got a third problem that we don't even have environmental weight limits. So we've got a lot of masonry arch bridges, and I'm a conservation engineer, care accredited, that need to be protected. And we've got no actual framework where we can kind of protect them a bit better in terms of maybe limiting the load on them or applying environmental weight limits. So we kind of got a catch-22 situation there. But one of the issues that I've kind of want to kind of try and highlight in relation to this, looking at the 3D analysis side of it and then bringing that down to level 2 and level 1, is on the level 3, and especially looking at the effects of spandrel walls. One thing that needs to be taken into account on quite a number of bridges is quite often you'll go out and inspect these, and one of the spandrel walls you'll be seeing a crack underneath the bridge, but the other spandrel wall you won't be seeing anything. And then you kind of start to look at the orientation of the ridge and you realise, oh, hold on a minute, that spandrel wall is facing due south. It's constantly being bombarded by the sun during the day and then kind of having the reverse in the evening. So it's expanding and contracting significantly more than the underside of the bridge, which is kind of a lot thinner, and the other spandrel wall. And it's kind of a question whether that should be kind of brought into the model at all or not. And then the other one is obviously intervention and the effect that that has on these masonry arch bridges, especially incorrect intervention.
I'll take the last one. I think that's easier. In relation to interventions on spandrel walls, so in Network Rail, we take a view that it's quite an expensive thing, and it's not about introducing heli bars and tie bars, and that takes the problem away. What it does, it actually carries the problems elsewhere. So we have a risk-based approach for dealing with this, and in certain locations, there are actually lateral restrictions that we put in terms of when track renewals are being done from our perspective as part of maintenance work, that the loading configuration as part of the track renewals is considered. And in the permanent case, if it's deemed the right thing to do, then that would be accompanied by a permanent solution. But we are not actively fixing longitudinal fractures in masonry viaducts. The issue about weather, I'm not sure, probably leave that to the researchers. I don't know if, Brian, you have anything?
Yeah, I mean, it's a very complicated and challenging question, I think, to be honest. So I'm slightly struggling with how to tackle it as well. But I think if you look at some of the examples in my presentation, where we've got bridges that are in good condition and well proven, they're pretty much okay. And actually, most bridges are in that state and we can ignore them. But we have this habit of allowing bridges that are in good condition to get into bad condition. And I think in your case, the Irish example there, the obvious mechanism for that is allowing heavier axle loads to pass the bridge than it's capable of accommodating. With network rail, again, the other example, the spandrel walls, there could be thermal effects, it could be scour, it could be all sorts of different things that cause this. But we need to get smarter about preventing the good bridges from getting into bad condition, because the bad bridges, we will be into complicated 3D analysis and monitoring like I was showing, and the sort of forensic stuff where you're trying to tackle a known problem rather than just maintaining it in a base state. So we've got to keep them in that state. And I do think one of the things that was quite good that was introduced through the Syria C800 was this idea of two different limit states. So we're not just trying to prevent things from collapsing, we're also trying to look at a limit state which is to prevent damage. Now, I've no idea how successful that's been in real life use or adoption from clients, but I think it's really important. It's quite rare in my practice that I get to have a conversation with a client where they want anything other than one answer. Is it safe? Do I need to close it? I mean, the RAAC debacle that's going on at the moment has been allowed to get into that position for want of early intervention. It's been allowed to get to a state where clients have only got one kind of possibility because it quite clearly isn't safe. We've got to avoid doing the same thing for masonry bridges. And I think if we can present a range of answers, this is where you might avoid damage. This is where you're going to get into damage, and you might have 10 years before you do something about it, but you are going to have to do something major surgery. We need to find a way of having those more intelligent conversations and keeping as many bridges at a lower level as possible. I don't know if that addressed any of it or not, but it was quite a long question to start with.
Anyone else?
I was wondering what the panel thought about recruitment. So we find it quite difficult sometimes to recruit senior and experienced assessment engineers. Really not taught at university, and certainly when I left university, I didn't know much about assessments. It was more the sexy design that I was certainly interested in. And I'm certainly seeing that, trying to recruit experienced senior assessment engineers. I was just curious to know, what do you think we need to do as an industry to entice people into this world of assessment engineering?
Good question. So basically, there are a number of things that we can do, and I've got my colleagues here, and I agree with the sentiment of actually going out and finding experienced engineers. They are not available, and I think the steps that we are taking is more making the engineers for the future ourselves. So sort of up north, we've gone into some sort of alliance with some of our suppliers where some of our engineers, we're sort of encouraging cross-pollination, where some of our trainee engineers we send to work in those consultancies, and then they also send their engineers into us, so that the whole idea is they come out on the other side, understanding the challenges that the client has to go through when you're making recommendations saying a structure is substandard, full stop. we are sat with the risk, how do we make decisions on the back of that? And then taking into account the whole sustainability, which ones comes first in terms of remediation and everything else. I also think that there is a call on all of us as a collective to make assessment a thing. So when you go about recruiting graduates from universities, for example, are we taking the opportunities to show the breadth of experience that they can have by being involved in assessments? So architects will show you very pretty buildings that will attract some engineers who want to be involved in some of those swanky, I call them swanky projects. But then in the same way, if we are looking to get to the net zero and the big aspirations that we have as an industry by 2030, that means we need to be very proactive about how we manage carbon emissions. A lot of our viaducts already have embodied carbon in them. And I'm not only talking about masonry, it could be metallic structures as well, where can we go into strengthening, for example? And that's a fantastic skill set for a new graduate coming out of university, being involved in this. And actually, it's reverse engineering. So you understand the design and then the retrofitting, as opposed to the situation where you've got a blank canvas and you are building something new. So I think as a collective, we want to bring visibility, bring some spotlight to what we do. Network Rail, we are looking to do more, but we can't do it all on our own. We really need all of your help in getting the message out there. We'll take any opportunities there are. If you're embarking on a recruitment campaign, we can buddy up with yourselves as an industry leader to make a case for, and it's also succession planning, isn't it? So we've got a bow wave of people who are retiring now, and the mantle is being handed over to us. So how do we make sure we retain that skill set in the industry? And I can go on and on. It's a subject that I'm very passionate about, but I'll let my other colleagues.
I suppose my thought on it is, we need to show that it's something that's valued. And we're beginning to do that. I mean, if you look at the I-Struct-T, the I-Struct-T have changed their awards now, so they're much more interested in issuing structural awards for retrofitting and things like that. I think, somebody mentioned conservation accredited engineers. I can't remember how many there are in the UK and Ireland. It's about 100 to 150 or something like that. Yeah, 60. It was more than that when I checked, but it might have gone down. But for the number of historic structures that people in this room collectively and our colleagues work on, it's an utter embarrassment that we think it's okay to have that number of engineers accredited to work on conservation structures. I've worked on several and I'm not conservation accredited. But what I will say is that was really rewarding work when I've done it. I felt valued. I felt that it mattered. So I think we need to feel valued, and I think to feel valued, we need to be valued. That's the harder part of the equation, because we're not valued until something goes wrong. Again, with our AAC that's in the news, and even then we're probably not valued. But we should control the bits we can control. So I think award schemes, I think recognition, I think qualifications like the CARE thing. I think we should find the opportunities we can to show that what we do is valuable. Maybe the financial bit is harder. I think we know that it is. But let's pick on the ones we can and get that message out there.
Just to comment on this from a university perspective, just anecdotal evidence, but my final year projects to do with assessment are way more popular now than they were 10 years ago. And the climate emergency is a key part of it. And the realization that we can't just carry on building more and more. We've got to actually get more from what we've already got. So I think maybe you'll find it's a diminishing problem in the future.
Hi guys, Callum from AIM Group. If we zoom out a little bit and look at the sort of more challenging portfolio level, what pieces of information are you guys missing that would really help focus, ever more constrained resources, finances on protecting growing issues or as Brian alluded to, preventing those sort of medium-term healthy assets from slipping into those one of the far more expensive schemes? What tools are missing? What information that would be useful to have as an industry?
Yeah, I think for arches, the unknowns is what's buried, what you can't see. So tools to be able to non-destructively see how the arch is constructed, the thickness of the barrel, those are useful. And we have used GPR to estimate barrel thicknesses and to some success, but it's, you know, we could do with more accurate tools, not easy.
I think for us, so we have our bridge condition marking index, and I imagine on the highways you've got same. We'll be in a very good place if we can actually merge our understanding of condition and capability. We're far away from that. I don't know through this research whether there are recommendations coming on how we capture consistently asset condition, which can then be input into some of the tools or models to accurately tell us what the capability of these assets are. That is a growing concern for us. The other one relates to just the general degradation of assets. So available models aren't as effective, if I should use that word, in giving us a sense of as masonry is deteriorating, at what point it actually goes over a cliff. And you know, with the fiscal constraints that we are all working under, it's, you know, just putting sticky plasters on there. But if we can have a clear understanding through this research, how much in terms of years we've got to intervene when, then that potentially will put a bit of urgency on what we do and then make our case more credible when funding is being sought. And I know it's a very difficult economic situation that we are under, but anything to improve what we currently do will be most appreciated.
Say that there is a two-way communication here, that both you have to learn a lot from the university, but I also feel that the university have to learn a lot from the industry. So having a workshop like that is extremely important. How do you see that we can link closer, like the university link closer to industry? For example, can you involve us when you're doing like any collapse of a bridge? Can we participate in activities like that? Can we contribute our thoughts? And do you know any mechanisms that we can work closer together to solve some of these challenges? This is open to everyone, but also to the panel.
I don't have any answer to that. I certainly think it's worth doing. I think, and I think it requires more long-term relationships, perhaps. You know, so I think between particular client bodies to have academic partners who they can call upon in a longer term sort of way, and involve in a series of work. You know, a series of projects rather than necessarily just you know, here's an opportunity to come to site for a nice site visit and solve one particular problem. Because I think on individual projects, the commercial arrangements and things very often just work against it. No one wants somebody else coming onto site who's going to throw another angle on it. We've got enough angles, which is why I think those long-term relationships, long-term learning relationships are worth doing. And I think a lot of big clients, I mean, Network Rail being a very good example, have a lot of assets and have an awful lot of data about them, which I think is underexploited. You know, if they've got tens of thousands of arches, all or almost all of those will have been through a level 0 assessment. There are a lot of numbers out there that it would be good to engage with the academic world and say, what can you make of this? You know, what can you do with it? What can you use with this? Use this information for?
Thanks. Synologicos, University of Oxford. So I think you mentioned something about data, and this is what I was going to ask. So do you see, what role do you see for data going ahead, thinking that it's changing some other industries at the moment? We haven't talked much about data today. I wondered if you've got any thoughts on that, and at what level do you envision using data to change the bridge maintenance practice?
So that's something that I've talked about with my colleagues. So we've been doing assessments for years on end, and we do have bridge capability information. It's data that we've not got the wisdom out of it. So there are opportunities for us to understand what we've got and if there are any emerging trends apply. It's just that we are working through a certain hierarchy, but it's not to say that the opportunity is not there for us to exploit what we have. So we'll welcome any proposals from a university to help us. Yeah, we won't say no.
Say with the emergence also of artificial intelligence and machine learning, I think is a natural way forward and perhaps the next step. So again, there is a clear indication that we need to work together, universities and industry together, and identify opportunities to tackle challenges.
Hi, Austin Richards from Gwynedd. I just thought I'd say, jumping with what Brian was saying, we have a third of our stock are masonry arch bridges, and half of those are listed, and they are possibly the best structure we have in the network. But one of the issues we have, I feel, in the industry is that there's a resistance generally to come out of the safe bubble of what we know. So how do we as an industry change and start embracing all the technology, or getting people more comfortable in doing this instead of saying, no, we haven't got 20 years of experience doing this, so we're not confident in signing that off. What do we need to change in the industry to tackle the climate emergency and start building masonry at bridges, I suppose?
Well, I suppose you need an intelligent client that's got things outside the box. And I suppose in our situation in the council, often we can do that, whereas perhaps highways agency and network rail are more bound by rules. So that's one chance, but so we can actually take the lead, I guess.
I mean, so we are embracing technology, and if you are you read the NCE magazine, every now and then you see people on LinkedIn, you see people trialing different things. In our world, for example, underwater exams were traditionally, somebody wades water with a rod in hand, looking for holes within that. As you know, it's fraught with a lot of safety challenges with that. So gradually we are taking on board the use of submersibles, like robots that go in the water, and that is giving us consistent data. But then there's the scalability of it as well. So, doing them as a one-off, obviously they're expensive, but if we can get to a place where we are specifying volumes, then obviously it becomes cheaper. So through our technical requirements as part of our examination contracts, gradually some of these are being introduced as a requirement for suppliers to bid, and we have expectations that we implement available technology where it is to help us. So we are open to the opportunity. The main thing is it scalable? Because you may have also random things that are being thrown at you, and it's fit for one situation, but you can't extend it to others. So we need to be wary of those as well. But it's something that we advocates of, and our leaders, as it were, are pushing the message. So for example, in examinations of lattice towers, previously somebody will turn up, you'll spend time taking the possession, erecting scaffolds and what have you, and it's time that is wasted. Could you use drones? And drones aren't the answer to everything, but in certain locations they are. We're also piloting what we call photogrammetry examinations, where we are combining drones for very tall viaducts. So using drones footage to capture all of that data to inform decisions that are made by asset engineers. So all of these things are gradually coming into the main, and we need to be open and take the opportunities they present.
I'll take one last question. Brian was.
Yeah, I was just going to say, I mean, as an industry, we pay people not to take risks. So if we want people to do things differently, we have to pay people to take risks. And to do that, we have to value the outcome of that risk. So the example here with the drone inspections, it's because, you know, we're saving time, money, safety risk on the railway. We can see very clear outcomes. If we want to go around building lots of new masonry bridges, you know, what's the good outcome? And if the outcome is lower carbon, we need to demonstrate that, and we need to value that, and we need to find contractual ways of valuing it, because otherwise it quite clearly won't happen, because it quite clearly is risk, because there are risks around competence and technology and all the rest of it that go with it. And I think that the environments quite often where we can manage risk are the more collaborative ones. So a lot of the project work that I showed briefly in mine was done under contractual alliance. So everyone shared risk, literally shared all the financial risk between the client body, Network Rail, the contractor, ourselves and others. And we got so many new things done on that project, you know, because people could see that connection between value and the ability to manage the risk. So we did clever things with BIM because we knew we could save time, because people could see it on the bottom line. And it wasn't just the contractor's problem or the consultant's problem or the client's problem. So different commercial arrangements and understanding what the value is we're going to get out of it. Without those two things, we will not be doing anything new. You know, I think that's pretty straightforward.
Okay, one very last question.
Just coming to repairs of masonry art structures, I work on the railway and in the railway industry. The standard suite of repairs that Network Rail have, and I don't know about in Wales, how effective do we feel they are as in dealing with the way a certain structure behaves, i.e. we do the repairs, but all the main fractures, they reopen or they reappear. And how do you compensate for that or deal with that, Brian?
I don't know why you're asking me. I'll just say from my perception, which I think is that we don't know. You know, it's the short answer. I mean, there was a structural engineer friend of mine shared on LinkedIn recently some photos. It was one of the Network Rail, Ouse Valley Viaduct, something beautiful railway viaduct, absolutely covered with patched brickwork. Must have been repatched 50 times, it looks like, looking at all the different colours of brickwork over it. Yeah, and I guess we know it's okay because none of the bricks falling out and trains are still going across. But do we really know how it's working or whether it did what they hoped it was going to do? You know, probably not really. So I think that kind of post-construction monitoring and evaluation we're really poor at, because we think we know what we're doing. We think we know how to fix this stuff, and we walk away and come back in 10 years' time and fix it again. So I think a program of evaluation of repairs, I don't think it's ever been done, has it? You know, in this area. I got an interesting response, but yeah, and I think again, it's got to be recognise the number of academics in the room. It's got to be another really good opportunity for an industry, academic, client research project. How effective are these things? Can we measure it? Can we prove it? You know, I'm sure there's knowledge out there that would help with that.
Your point is valid in terms of the effectiveness of repairs. So I know Basam is helping us with so before we go into actually doing repairs, do we know what is actually causing it? So I think there's some work on fatigue in certain respects and damage in masonry arches that we are hoping would inform our standards and the sorts of intervention that we are putting forward. I mean, installation of heli bars, and suddenly over a few years it opens up again. We are spending a lot of money throwing good for bad. And that's why we've put this challenge out there, and we're working with Imperial College to help us understand that. But I know in time the standard will change to reflect that. And I also know Bill Harvey Associates did some work on us looking at some of the repair solutions that we have in those standards. And I know they constructively put some comments out that we are looking to embrace. So it's not to say we do not recognize it. We know it's a challenge, and the efforts, at least the wheels are turning to bring some improvement along that.
Yeah, I think you know, where I've had to repair masonry arches, there's always been innovation. There's always been something new and different. So I suppose capturing that and having case studies, I'd say perhaps going back to it 5-10 years later to see how effective it is.
Excellent. Thank you very much. I think this is the closure then of the workshop. A lot of interesting ideas, a lot of concepts, a lot of food for thought. Thank you very much for this participation. Thank you very much to the panel also. I hope you have enjoyed the workshop.